All right, so this is maybe the hard part where the people that don't have too much math background start getting confused and start getting crazed, violent looks in their eyes, and it scares me as a teacher. So let's see if I can go through this without too much headache, but without also too much work on my part because I'm kind of lazy. All right, so let's say we have a case where we want to minimize portfolio variance such that the weights are going to sum up to 1. I don't need me here. All right, so let's see. We have a situation where we're going to minimize variance such that the portfolio weights are constrained to equal 1. We want to be fully invested in asset 1 or 2. Or we can also say that W1 plus W2 minus 1 has to equal 0. All right, so one thing we can do is we can plug in and put this into a Lagrangian form where we have the portfolio variance, the exposures of the assets times the covariance matrix and all that kind of stuff. And over here we have the constraint. And this lambda is a Lagrangian multiplier. All right, so this should end up being a negative number because if we increase our constraint from 1 up to a number 1.8, or if we force our exposure to the risky assets to go up, our variance should increase too. So as we have this -1 go up to -1.8, the negative change times the negative Lagrangian will lead to a higher multiple or higher value. All right, so to make things easy, I'm all about easy. All right, I'm going to say I'm going to maximize 1/2 of the variance. And this will not affect the coefficients for the weights. The weights that minimize variance will be the weights that minimize 1/2 of variance or any positive constant times the variance. Right, so I'm going to multiply this by 1/2. And I put the 1/2s in there because when I take the first derivative, it cancels out nicely. So this Lagrangian multiplier is some value that we're going to solve for, and it's going to be just enough to force this condition to hold. So if the way to minimize variance over here without constraints is to hold no weights in either asset 1 or 2. So if this part right here gets too small, the difference between these weights -1 will become more and more negative times this Lagrangian, and so that's going to push up the value of our objective function. All right, so if this is negative over here, this lambda is going to be high enough to penalize our function. If it's too high, it'll be such that the circled area will be greater than 1, and so I don't know, that'll lead to some problems too. So what we're going to do is solve for this Lagrangian along the W1 dimension, the W2 dimension, and the Lagrangian multiplier dimension. So our objective function ends up being how we express our variance of the portfolio, and here's our constraint. All right, so we have the Lagrangian with respect to W1. All right, so there is a W1, so it'll be 2 times 1/2 times W1 times the variance, 2 times 1/2 times W2 times the covariance, and we got a W1 over here, so plus the Lagrangian. All right, so we do the same thing with W1 and dW2, and we also take the Lagrangian with respect to the lambda, which just returns our constraint. All right, so we can also say that if we set this equal to 0, we take the gradient of the Lagrangian and set it equal to 0. Okay, so one thing we can do is, I guess what we're trying to solve for is W1, W2, and lambda. So we can factor out the W1, W2, and lambda. So this expression right here will be the variance of 1 times W1, the covariance of 1 and 2 times W2, and 1 times lambda. And so we do the same thing with the second equation and the third equation. And these values over here, bring the 1 over there, will equal 0, 0, and 1. So we can solve, just invert this matrix on both sides and solve for W1, W2, and lambda. So it's easy enough to do that. So there's a way you can show that this bordered Hessian is positive definite. Just look in the notes on pages 35 through 40 of the MSF 501, 502. Hey, man, I've talked enough about calculus. All right, so I guess what I've done is it's nice to have use an Excel or R. So what I've done is I've created a vector of returns. I've created this vector of the covariance matrix, and one's on this side and one's on the other side. And so what I did is I solved for, solve is basically what this is the x inverse times 0, 0, 1 to get these portfolio weights. Okay, so cool, I found the minimum variance portfolio. So I can find once I find these portfolio weights, the utility, well, man, what is this function? Okay, so this is a minimum variance portfolio. So the minimum variance portfolio, the expected return is going to be 0.73 times 0.27 times the returns that I said were 10%, 14%. So we get an expected return of 11.06%, and the variance will be 0.73 times 0.27 times the covariance matrix, which would, in my example, I have 0.09, what is it, 0.05 is the covariance, and 0.16 times 0.73 times 0.27. That gives me my gives me my variance. Take the square root of that, and I get the standard deviation. All right, so that's that's Lagrangian multiplier calculus. So if we want to do this whole thing with calculus, we have 1/2 times the portfolio variance times this vector, where I'm going to say E is going to be a vector of ones. All right, so if I have a vector of ones times the weights, it sums up the weights. All right, so I do my little calculus here with the first order condition with respect to W using rule 3 is going to be the covariance matrix times W. Using rule 1, it's just going to be lambda times the row vector of ones. All right, so I can solve for W1, bring this to the other side, take the inverse of the covariance matrix. And so I can find this variable right here. All right, and so one thing I can do is I can use my condition of Lagrangian with respect to scalar lambda as being my constraint. And so I'm going to take this value and pre-multiply by E transpose, the row vector. And so by construction, that's going to equal to weight. So if I pre-multiply by E transpose over here, I pre-multiply by the vector of ones over there. And so what I do is I solve for the lambda. So it's going to be 1 over the scalar. And I plug this thing back into here. And then I get my mean minimum variance portfolio. So it's calculus, it's taking first order constraints, doing all this kind of stuff. It's pretty cool. And I hope this gets you caught up with where you should be. So if you MBAers got an English degree as your undergraduate, hey, I apologize for this material, but hopefully this catches you up. And if it doesn't, see me. All right, that's it. Peace out.